What specific problem does the MVoT method aim to address in the context of multimodal spatial reasoning, and why do traditional approaches struggle with this problem?
The MVoT method aims to address the problem of effectively integrating visual and verbal reasoning in multimodal spatial reasoning tasks, particularly in generating accurate visualizations that complement textual reasoning. Traditional approaches, such as chain-of-thought COT prompting and React-style pipelines, struggle with this problem because they rely heavily on separate visual modules or external tools, which limits their expressiveness and adaptability to complex spatial reasoning tasks. These methods often fail to capture intricate visual patterns and spatial layouts, as they depend on purely textual representations that do not align with human cognitive processes, which naturally combine verbal and visual thinking. MVoT overcomes these limitations by generating interleaved reasoning traces that include both verbal thoughts and visualizations, allowing for a more intuitive and effective reasoning process. This integration enhances the model's interpretability and robustness, ultimately improving performance in dynamic spatial reasoning scenarios.
How does the proposed MVoT method work? Please illustrate it step by step, particularly focusing on how the reasoning traces and visualizations are generated.
The proposed Multimodal Visualization-of-Thought (MVoT) method operates by generating interleaved reasoning traces and visualizations in a step-by-step manner. Initially given a multimodal input sequence, the model generates a sequence of verbal thoughts denoted as Z and corresponding image visualizations denoted as V. For each intermediate reasoning step, #Z_I, MVoT adds an image visualization, #V_I, which is conditioned on the prior verbal thoughts and visualizations, enhancing the reasoning process. This interleaving allows the model to create a cohesive reasoning trace that integrates both text and visual modalities, facilitating a more intuitive understanding of the reasoning process. The model is trained on these interleaved sequences, learning to produce multimodal outputs that reflect the reasoning process effectively, thereby improving performance in complex spatial reasoning tasks.
Can you provide a simple yet illustrative example that demonstrates how MVoT integrates visual and verbal thought processes during a specific spatial reasoning task? Walk through the main algorithm steps with this example.
In the context of the maze navigation task, MVoT integrates visual and verbal thought processes by generating interleaved reasoning traces that combine both modalities. For instance, when the model receives an initial maze layout as an image and a starting position, it first generates a verbal thought, e.g., move right as the first step. Simultaneously, it produces a corresponding visual thought that illustrates the agent's movement within the maze. The next step involves the model sampling a new verbal thought based on the previous verbal and visual outputs, such as, now move up, while also generating a new image visualization that reflects this action. This iterative process continues, with each step conditioned on the prior verbal and visual thoughts, ultimately leading to a final answer that indicates the agent's destination. By employing this method, MVoT effectively enhances the reasoning quality and interpretability of the model, allowing it to navigate complex spatial environments more intuitively.
What are the theoretical and practical benefits MVoT offers over traditional chain-of-thought COT methods? Can you quantify these benefits based on your experimental results?
Theoretical benefits of MVoT over traditional COT methods include its ability to seamlessly integrate verbal and visual reasoning, allowing models to generate interleaved reasoning traces that reflect human-like cognitive processes. This multimodal approach enhances expressiveness and interpretability, addressing the limitations of COT, which relies solely on textual representations that often fail to capture complex visual patterns. Practically, MVoT demonstrates superior performance in spatial reasoning tasks, achieving over 20% improvement compared to COT in challenging scenarios, as evidenced by extensive experiments across tasks like maze, mini-behavior, and FROZENLAKE. Additionally, MVoT's incorporation of token discrepancy loss significantly enhances visualization quality, resulting in an average of 95% correct visualizations during reasoning, compared to lower accuracy without this loss. Overall, MVoT not only improves task performance, but also provides a more intuitive and effective reasoning framework for multimodal interactions.
How has the MVoT method been validated or tested? What datasets were used, and what specific metrics or benchmarks were employed to evaluate its effectiveness?
The Multimodal Visualization-of-Thought (MVoT) method was validated through extensive experiments across 3 dynamic spatial reasoning tasks: maze, mini-behavior, and FROZENLAKE. These tasks were designed to assess the model's ability to navigate spatial layouts, interact with environmental elements, and recognize fine-grained patterns. The datasets for these tasks were constructed to encompass varying levels of complexity in patterns and action spaces, with specific statistics provided in the paper. To evaluate MVoT's effectiveness, several metrics were employed, including visualization accuracy, VACC, visualization pattern redundancy, VRED, visualization correctness step, VSteps, and visualization correctness ratio, VRatio, which collectively measure the quality and accuracy of the generated visualizations. Experimental results demonstrated that MVoT outperformed traditional chain-of-thought (COT) methods by over 20% in challenging scenarios, indicating its superior adaptability and robustness in complex spatial reasoning tasks.
What are some limitations or potential drawbacks of the MVoT method, particularly in relation to its application in complex spatial reasoning tasks?
The MVoT method, while innovative, has notable limitations, particularly in complex spatial reasoning tasks. One significant drawback is its reliance on the quality of image tokenization and generation, which can lead to inaccuracies in visual thoughts, as evidenced by the observed blurring of details in generated images for tasks like Frozen Lake. Additionally, the model's performance can degrade without the incorporation of token discrepancy loss, which is crucial for aligning visual and textual embeddings. Without it, MVoT may produce redundant patterns and fail to accurately capture state transitions. Furthermore, the complexity of the visual patterns in tasks can overwhelm the model, resulting in a loss of fine-grained details and inconsistencies between generated and original images. Lastly, the interleaved reasoning process may still struggle with the intricate visual patterns and spatial layouts that are often inherent in complex multimodal tasks, limiting its overall effectiveness.